All right, so hey everyone, can you hear me? Like raise your hand if you can hear me. Raise your other hand also if you can hear me. Like people not raising hand, like what's happening with you? Anyway, cool. Welcome to the Bangalore Paper Club. This is edition 2. And thank you so much first of all for Lightspeed to provide this like beautiful space. I hope everyone is settled in, have their drinks in hand, and then let's just kick things off. Thank you so much for coming here on like a Friday night. I understand there are like many things to do on a Friday night, and you guys decided to come and sit in an hour-long lecture that can also extend to 1.5 hours. We are already running like 15 minutes late, but yeah, I think that's completely fine. Cool. So, what this is all about? Oops. The first one was so nice we had to do it twice. So we started the paper club with the objective of just like trying to increase the people getting into research. I'm pretty sure like a lot of people are doing a lot of things over here, and it's just that research seems like a boring topic that okay, it's a paper, it's like 10 pages long, let's not read it. We're all like just using some APIs, just get it, put it in our harness, run things around. I think that's great, but end of the day we just decided okay, we watch a lot of paper videos, like YC Paper Club is the inspiration for all of it. And then we kind of decided that, okay, what if we did it here also? Nobody needs to travel to the valley to do it. And kind of blew up. We recorded the first session, we put it on YouTube to figure out like, okay, how do people receive it? And it's been like about 10 days and we got like about 15,000 views on YouTube. We got like 2,000 plus subscribers coming in. And if you search for Paper Club, like we rank above. I'm not sure if it's geography or algorithm or whatever, but like I'll take that as a win. Getting back to it, the objective was to meet researchers in real life, present papers, discuss interesting problem statements, and work together on some of them. And we got a lot of requests that, okay, we started the first edition as a pilot, so all the papers were presented by my team. And this time we decided that, okay, let's open it up for other people also to come and present their research, what they have been up to. And this time we have 2 people coming in, super interesting papers. We'll talk about it when that comes. But we have like some other people coming in as well, and this is something that we'll continue doing forward. The idea is to talk about AI, but not just from like a SaaS perspective or like an agent perspective, but how AI affects other domains like, I don't know, supply chain, healthcare, other things. A little about myself. My name is Kautup. I'm the founder of Conscious Engines. Conscious Engines is a research lab. I'll talk about it in a bit. So yeah, that's us. We build domain-specific language models for enterprises. So the idea is to build small, specialized language models. The North Star that we work towards is that as intelligence saturates, cost per outcome becomes the thing that matters, not model size. So you can do more with less, and that is where we kind of like come in. Cool. That was about us. Now coming back to what Bangalore Paper Club is. So as I said, it's super inspired by YC Paper Club, and then we keep looking at their videos. We are better than them that we have like a bi-weekly cadence. They keep doing things, but again, like they are them. So we'll get there eventually. All of this, again, like show of hands, who all are part of Research Room India? Nice. So this is a group that we started because we wanted to get our papers peer reviewed and also like get some people to endorse us for archive. I think we got it like successfully done, but now the group has like about 823 members with like 105 pending, which I am like just procrastinating on adding them. But we have close to 1,000 member community, and then we keep discussing about frontier papers, whatever's coming out, and then like doing events like this from like interest. Today's agenda. So we will be talking about LLaDA, which is large language diffusion models, one of the initial papers. This is something that we are essentially looking at as well. And since our objective is diffusion language models, these are some 2 things that my team would be talking about. The second paper is called Nemotron-TwoTower. This is a paper that came out like a couple of weeks ago. It's an efficient architecture for diffusion language models. It uses like 2 stacks. The third one is by someone outside the team. His name is Soham. Soham is here. He's a researcher at Servam, and he'll be talking about graph language models. And then finally, one of the most interesting papers I came across like recently, it's called Diagnosis. The idea is to detect cancer. Like, can dogs detect cancer through smell? And turns out they can. With that, let's begin. Sorry, that's supposed to happen later. So I would invite Rishi to talk about LLaDA.
Hi everybody. Before we start, just a quick, has anyone heard about diffusion language models? Have you all gone through the idea? Oh, okay, great. Oh, wow, amazing. So I'm then very excited to introduce this paradigm of language models to the rest of you all and hopefully add something to the knowledge of people who are already aware of the field. I'll slowly start by introducing diffusion language models and comparing them to autoregressive models, which is what every frontier model in the world currently is. Your GPT, Claude, Kimi, etc. are all autoregressive models. LLaDA was the first large language diffusion model of its kind that was introduced last year at NeurIPS. This is an 8 billion parameter model. It was pre-trained on around 2.3 trillion tokens and fine-tuned on 4.5 million SFT pairs. This changed how we look at diffusion. Frontier image models in the world are primarily diffusion based models, but there have always been issues to bring that tech to text. If you think about how a diffusion image model works, let's say you're generating an image of a sky and the tone has changed from light blue to a slightly lighter or darker blue, it's not that much of an issue. But if you bring this to text and cat becomes chat, then that's a large issue. Diffusion models inherently work by introducing noise, training on introducing and removing noise, and that's what happens at inference time. So it's critical for noise to sort of leave the system while you're inferencing, otherwise it's not a usable model. Right. So staying on theme with our autoregressive versus diffusion comparison, autoregressive models generate a token at a time. So if I want to say Paris is the capital of France, it is Paris is the capital of France, right? Whereas mass diffusion models, which is what LLaDA is, starts with a fully masked sequence. Yeah, okay. Starts with a fully masked sequence, and then progressively you have things called denoising steps. It's a set number of denoising steps, which means your computation will finish only in those many forward passes. And then by the end of the set number of denoising steps, you are masking and remasking tokens till finally on the last step you have unmasked all your tokens, right? So because of this architecture, autoregressive models see only the token to their left, which is the previous token. Diffusion models can see tokens on both ends if they are unmasked. Autoregressive models predict only the one token to the right. It's technically just a next token generation machine, and the order is 6 from left to right. Diffusion is not bounded by these rules. Right. This is a quick animation to show what training looks like. You essentially start corrupting your data. You have a sentence and you keep on randomly corrupting words of your sentence. This is how data is noised and then later denoised. That is your entire training loop, and it is uniformly noised. And this is what it looks like during inference. You start with a fully masked sequence, and then you start committing positions as you go down your denoising steps. If you fix your denoising steps, so let's say 8 denoising steps, then you will be fully unmasked by the 8th step. And the way this works is, you have a fully masked sequence, you start by unmasking them. When there is a probability of a certain unmasked token, and if the probability is high enough and above a threshold, then that is committed and will no longer be masked on that step. So on the next step, if there is a low confidence probability of a previously unmasked token, then it can be remasked as well. Yeah, the objective of this is to hide tokens at every difficulty. The model should know to recover from every semi-masked or semi-unmasked sequence along the way. This is the primary difference when you compare this with something like BERT. BERT is language understanding reconstruction sort of a thing, where it understands, it masks, let's say 15% of the tokens of the entire sentence, and it understands language representation in the way of demasking. It will not be able to recover if you give it a fully masked sentence and just ask it to generate. These are some benchmark numbers that LLaDA reported in their paper. This is LLaDA versus Llama 3. I think this is Llama 3.7b. So on MMLU, GSM8K and human eval, it sort of beats Llama 3 with a decent enough margin. And the one place where we see it sort of not stand up is BBH, which is a short Python generation benchmark. Yeah. Now, by just following the architecture that diffusion language models have, they would obviously have less direction bias, right? If you can see tokens on both your left and right, that equips you to go both ways and not just one way. For example, there's a very interesting task, which is, can you write a poem frontwards and backwards? So GPT-4o is really good at writing it in the forward sense, which is 82.7%, but you ask it to write it backwards and it sort of does not understand the task. Whereas LLaDA, on the other hand, while being magnitude smaller than GPT-4o, is way better at writing a reverse sequence of tokens. And again, another inherent feature that you gain by having this architecture is infilling. Let's say you have a tool calling model, or let's say you have a certain JSON schema which is fixed, and all you want generated is the content of your JSON schema. That is something we call infilling. So infilling will obviously also be a lot better with this architecture, because you can see bidirectionally. It's not causal, you can see bidirectionally. So you can see LLaDA has a 73.8, whereas Llama has a 73.3. LLaDA is a much older architecture. This gap is now a lot larger for infilling. Right. And the primary reason why people are excited about diffusion language models, and it seems to be the next norm or frontier, is speed. While there is no sort of fixed length to how many tokens an AR model will generate, it will sort of keep going till it reaches its end of sequence token. You can fix the number of denoising steps for a diffusion language model. If I say I want an 8-step denoising pattern, I get an 8-step denoising pattern. I know almost exactly how much time that's going to take. And by the end of it, I will have a usable sentence if the training and post-training has been done well for my purposes. So if you look at the speed benchmarks, it's 1.5x to 1.8x throughput. On tougher benchmarks, I would say, like math and GSM8K for the time, human eval is matched, and there is a small lag for MBPP, which again has been fixed by the future generations of diffusion language models. Yeah. So we've obviously spoken a lot about autoregressive. It commits a position at a time. LLaDA comes under the third category, which is a pure diffusion or a fully masked diffusion. This is when your initial state is fully masked and you keep demasking. The current norm for diffusion language models is something called block diffusion. One main drawback of diffusion language models is that you have a fixed canvas length. I can commit 256 tokens, 512 tokens, 1024 tokens, or even more. But whatever the number is, it has to be committed before time. So if I don't know exactly how long my task is going to be, I can run out of space. And this happens, or happened, quite a lot. If your canvas length is too long, you're wasting compute. If your canvas length is too short, you will get cut off. Block diffusion solves that problem. Block diffusion sits in between autoregressive and purely diffusion models. You are able to now set a block size, but not the number of blocks. So you have a fixed block size, and a block is denoised together, and then you move on to the next block. That is where the autoregressive part comes in. It is a block after a block, but everything within the block is still extremely sort of diffusion DNA. Extremely sort of diffusion DNA, and it gets processed at the same time. Right. So let me compare everything that this paper had sort of put together. It did have a fully matched model scale. They had a smaller version of LLaDA, which is 1.5 billion parameters roughly, and they compared it to a Llama 1.5b that they had. So that's a great sign on like fully matched models. The flagship result, however, they compared the LLaDA 8 to the Llama 6.83 effective. So slightly taking those results with a pinch of salt. But on the flip side, LLaDA was pre-trained on just 2.3 trillion tokens, whereas Llama 3 of course has 15 trillion in its pre-training data size. This doesn't mean that LLaDA is 6 times more data efficient, because there are a lot of other factors to consider here, but it's great signal. On inference side, as I said, the canvas has to be chosen beforehand. The authors found that 256, 512 and 1024 are the most effective canvas lengths, and that is what they primarily use for their benchmarks. And 332 to 256 passes or denoising steps is what they recommend as well. Great thing to note here is that LLaDA did not have any sort of KV cache. So all these numbers which I've spoken about, while Llama was served through VLLM with optimizations and KV cache and all other tricks that we use for memory efficient serving, LLaDA had access to none of those. Now, however, we do have variations of KV cache, other runtime optimization techniques, which bump these numbers up significantly higher. So yeah, even when you come to post-training, though it did have 4.5 million SFT pairs for fine-tuning, no RL was done at all, there was no preference alignment or anything as such. Another interesting thing that happened while benchmarking LLaDA, they gave numbers across 5 benchmarks, but as I said, if you have a fixed block length and your answer is finished before your block length is done, then you have end of sequence tokens. They had trained so much on smaller sentences and sequences that the model was extremely eager to predict an end of sequence token. So even though it had the intelligence, when they were running longer benchmarks, they were hitting end of sequence tokens really quickly and the answer was sort of stopping itself. So they had to manually go in and sort of reduce the confidence of end of sequence tokens so that it could be remasked in the next step, if you remember that point. So the little bit of manual intervention was required here, and I think they also put out a fix soon enough to cover this up. So yeah, this is the story of diffusion language models. This paper primarily proves the point that language models can scale and don't have to commit to a left to right sort of sequence, which is something we're so used to because English and most native languages are left to right written. We are very used to this sort of tokenomics and linguistic, but it is great that we see different paradigms, non-human paradigms when it comes to language, also step up and probably go on to be faster, better frontiers. Thank you.
Next up, we have Hari. He will be talking about the TwoTower paper, which even improves further upon the diffusion language models to speed it up even faster. The idea is that right now in diffusion models, the context understanding and the denoising step are taken care by the same component. However, this model kind of like splits it into 2 parts, and this kind of like allows gains of like up to 2 to 2.5 times the speed of like a regular model. So yeah, Hari, please.
Hi, I think Rishi gave you a very good understanding of like how diffusion models work, and sort of like a comparison between AR and diffusion. So this paper from NVIDIA, a few weeks back it came out, kind of sort of like combines the benefits of an AR model and the diffusion model together. So if you guys have been working in the domain, AR or like diffusion models using both, you might have seen that the main issue with autoregressive models is the speed, of course. So yeah, the obvious choice is okay. Let's say we build a diffusion model with the same training set and everything. Can we get the speed improvement over AR models? Yes, you do get that. But the issue is diffusion models are still not as good as AR models in terms of accuracy. So they are like almost 98, 97, maybe 96% accurate compared to the AR models. So NVIDIA thought, okay, why don't we just combine both? That's what they did. So can we adapt the strong pre-trained AR backbone and use the diffusion models denoising process, which is super fast, and this does not sacrifice on quality. Yeah, so the problem with single network diffusion models like LLaDA, or let it be block diffusion model, still it has this issue where it has to do 2 roles at the same time. Role 1 is context representation. So basically, it has to encode the prompt and already committed tokens, and then it should understand, okay, this is the context. Okay, I'm going to generate the the upcoming tokens, and then it should be coherent with the context. The role 2 is iterative denoising. So it should do the denoising process iteratively, and then it should generate coherent text. So these two things are handled by the same network. Now, there's an issue here. So the context thing, AR models are natively good at doing that. So that is more like a causal AR modeling issue. And role 2 is basically bidirectional denoising. You can do denoising as fast as possible in a bidirectional way, and you can get the speed advantage. So when you do both these roles at the same time, when a diffusion model does this, it doesn't get the accuracy that AR model gives us. So the core idea of this paper is using two networks parallelly, and that's why the name two-tower. So yeah, before going into the two-tower architecture and how it works, let's refresh a little bit. The same things that Rishi has covered. So mass diffusion. The idea is that you replace tokens with special mass tokens, and the model learns to reverse it, basically demask it, and the corruption of token, let's say token X at block B at position L, is based on this particular equation that you see here. So it has like two terms. The first term here is basically saying that what is the probability of a completely unmasked token, and this is the probability of a completely masked token. And here, as just there was a discussion here regarding the schedule of noising. So here they used linear noising. So basically, the idea is that given a completely unmasked token, what is the probability of producing a masked token? And let's say the T is the step at which the noising, the amount of noise that is being applied. If you completely give maximum value for T, that is basically 1, it means that all the tokens are masked. If you give very low value, 0, it means that everything is unmasked. So this is the probability by which the masking happens. And block diffusion, what it does is it kind of like does the autoregressive part where you're not completely having all the tokens unmasked at the same time, but you have blocks of tokens which are like sequentially unmasked. Now, this is the two-tower setup. Basically, you have two networks. The left one that you see here is the context tower. So these two networks share the exact same parameters, initial parameters. So these were trained on some big corpus data. I'll come into the details later. But yeah, so they the same architecture, same parameters and everything. The AR or the context tower is what gives the context or the understanding of, okay, this is what the context is about, and you can use my information to do the denoising when you're about to do the denoising. So how it does is, the context tower works in an autoregressive manner. So given a context or a set of tokens, it produces the future tokens in an autoregressive manner, just like a normal AR model. And the denoising tower basically does diffusion. So it will do block diffusion. It will take mass tokens and it will try to denoise it. Now, there is some tricks or like hack that are done here. So the context tower is completely frozen. It's not trained throughout the entire training process of the denoising tower. The denoising tower has trainable parameters. And there is something very interesting happening here. They share something. So they share the KV cache. That is where the context comes from. They also share the Mamba states. Now, there is a bit of like hack they have done here. What happens is each time a new block is being processed, they copy the Mamba states from the AR network to the diffusion network or the denoiser network, and then they start doing the denoising process. And they also do cross attention from the context network to understand the context through cross attention and then process it. So this is how both are connected. And again, the context tower is completely frozen, it's not trained. So yeah, getting into the details, architecture details. So the pre-trained backbone or the AR network is basically a Nemotron-3 Nano 30B model. It's a hybrid Mamba transformer mixture of experts model with 23 Mamba layers, 6 attention layers, total 30B parameters, but 3B active. Now, one important thing is, the AR network processes the prompt and every committed token that is given by the denoiser. So it will process everything, and the AR network is already pre-trained. And the role of AR network is to produce KV cache from the attention layers and Mamba recurrent states from the SSM layers. and weights are never updated, and it retains the LM head. So this is something that they've kept so that later, let's say we are planning on doing speculative decoding or verification or something, we can use the LM head. Now coming on to the denoiser tower, it's the same structure, everything is same, initialized with the same pre-trained weights. The only thing is they do bidirectional self-attention because now it's diffusion, not autoregressive. So you don't have to do causal attention, you can do bidirectional attention. And between the networks, when they are doing cross attention, they do causal cross attention because you are attending from AR network. So there it is autoregressive. You don't want it to see the future tokens. So yeah, so it's like bidirectional self-attention plus the cross attention is causal. They do one more interesting thing, which is time step conditioning. So this is where they use adaptive layer normalization, and they have a small subnetwork of 1.5 million parameters, which gives them the parameters for layer normalization, adaptive layer normalization. And they did an ablation. With this, they get some performance improvement. I'll come to that. And yeah, the Mamba layers stay causal, so it is left to right, it doesn't go the other way. They did an ablation on that too, and it didn't give any performance improvement. And yeah, coming on to the intricate details of like how the attention between the the context tower and the diffusion tower works. So they do sort of like a cross attention between. So the key comes from the query comes from the denoising tower or the diffusion tower, and the key and value comes from the context tower. And how do they do it? So basically, they sort of like build a pool of all the KV caches from the denoising tower and the context tower. And when you are looking into this equation, you can see that the K values, which is the frozen cache from the all the previous clean blocks, like the causal way, from the the context tower. But when it comes to the diffusion tower, you can take all the K values because it need not be the causal way. And yeah, you take that. That's how the K is structured, and similar way value is also structured, and you basically attend to it in this way. So yeah, that's how the cross attention works. Now it is layer aligned. So what it means is sorry. So yeah, this cross attention works in their own respective layers. It doesn't attend to a layer that is not aligned to it. So basically, it goes from this layer to this layer, and yeah, so it doesn't do attention across different layers. It does that attention across aligned layers. So that is another important thing. So the understanding is that at different levels, each layer will encode some different understanding of the the decoding process or the word meaning or the context understanding, etc. So that's why it has to be layer aligned. And yeah. So basic algorithm, how it works is that context tower processes the prompt causally, and it gives out KV caches plus Mamba states. Then you initialize the next block. So basically you have some block size S and different mask tokens. So by default it is 16. There is an ablation on that too. And the denoising up to some T steps. Let's say if the block size is 16, you do 16 denoising steps and predict all the masked tokens in parallel. And then you commit. So once you commit it, you take that and give it back to the AR model, and then you continue this process again and again. So until the end of sentence or like the length limit is reached. So every time this happens, AR model runs once, and the two-tower, basically the denoiser, takes several steps to like decode or denoise the entire block. Coming on to inference, inference is basically done in this way. So there is a confidence level set of like 0.8. If it goes beyond that, like it is more than that 0.8 threshold, then those tokens are demasked and the others are set as masked. So this is how it is done. And what trend that they see is, when you start the denoising process, during the initial few steps, let's say 1, 2, or 3 steps, basically almost all the tokens, so like 90% of the tokens are being accepted. And as you go ahead, like as you continue the process, fewer and fewer tokens get accepted because it needs to find those difficult tokens, demask those difficult tokens, and it takes time. So that's why it starts from 6 to 12 tokens, and then it sharply reduces, and the mean is like 2.7 to 4.9 tokens per step. Coming on to sampling dynamics, again, the same thing. This basically shows across GSM8K and MMLE Pro that most of the tokens are accepted at the initial diffusion steps, ranging from 1 to 6. And as you go further, it basically reduces. So, two different ways to like represent it. Now coming on to the training objective. So this is classic training objective in all diffusion models. So this is mass diffusion training objective. So this is basically saying that what is the probability of finding an unmasked token given the context C, that is for all the previously demasked blocks, and at denoising step at T, and then the masked token, which is the ZT. So you take that probability, you take negative log of it, because we want to, sort of like minimize the loss so that you maximize the probability of getting an unmasked token. That is very correct. And then you average it across all the masked tokens only. You don't do it throughout all the tokens because you don't want to do it through the unmasked tokens. And that is the objective here. And it is very linear schedule, just like we discussed. And coming on to the training recipe, how the training setup was done for this. So there was a 2-stage training process, phase 1 and phase 2, where 1.4 trillion tokens were taken on like phase 1. It was a broad coverage blend of like data set. Then there is a phase 2 training of high quality data that comes from STEM focused domain. And a total of like 2.1 trillion tokens were used for training the 2-tower setup. Now, remember that the AR model and the denoising tower, which shares the parameters from the AR model, were already trained on 25 trillion token. So that is already there. So yeah, that is there. Then when it comes to optimizations, they use BF16 precision, and then Adam W was used. Then they took a warm-up stable decay sort of like learning rate, where it peaked at 10 raised to minus 4 and then settled on like 10 raised to minus 6. Then the block size here is 16, similar to the Mamba chunk size that they used. Then the optimizer is reset at phase boundary. So that is there because when you move from phase 1 to phase 2, the domain is different, the data set is different. So if you don't reset the optimizer, what happens is that it will be in some momentum and some direction in a different loss landscape because the data has now changed. So you have to reset it and then you continue the training process. Yeah, so the main result, quality versus throughput. You can see the quality is almost as same as AR model, but the throughput is like 2.42 times faster. So you see barely like less than 3 power points, like percentage points drop in quality, but yeah, the performance is like very good. Now, a small Pareto figure like showing that once you increase the throughput by reducing the step size during inference, what happens is like the quality reduces. That is obviously there because you trained it for like some 16-step denoising process with 16 block size or something, and then once you reduce it, it does drop in performance, and especially math and coding kind of like drops quickly. So that is there. Some ablations that they have done, specifically like design components. So they tried the baseline bidirectional attention causal Mamba 2-tower setup. They got some results. So they thought, okay, why don't we just try a bidirectional Mamba? So we are doing a causal Mamba. Let's do bidirectional Mamba. So they tried it and they didn't get any performance improvement or anything. So then they stopped doing that and they tried time conditioning, which is the equation that you saw, like when they use an adaptive layer normalization with time conditioning, they got an improvement in accuracy, like the performance. So yeah, all this was done with a step S equal to 32. And they did one more ablation, which is basically adding the phase 2 data. And when they did that, they got a very good performance improvement. So that is the final setup that you see in the paper. And ablation 2 is about like why 2 separate towers? Like why don't we just stick to 1 tower or like completely do something else with it? So they tried 3 basic configurations. First is the frozen context plus trainable denoiser. That is what the paper's whole idea is about, and they got the scores, so that's the best. Then they did an ablation with removing the denoiser, just using the AR model, and then they continued the training with the new phase 1 phase 2 data set and everything. So they saw a performance drop of like 10% to like 17% in math. So that is very bad. Then they tried something interesting. They tried tied weights or like joint AR plus diffusion. So what they did was they built a combined loss. So they kept the same way, context tower is there, denoising tower is there, but they kept the context tower unfrozen. So it's not frozen anymore. It can update the weights. Now the objective function becomes the loss of the context tower, basically the objective of AR plus the objective of diffusion, both combined. Now this combined loss was used to backpropagate and update the weights. Now this was very bad. So it went to like 26% performance, like the percentage points, like very bad. Now coming on to block size ablation, they tried different block sizes and they saw that 16 is the ideal block size for like very good accuracy. Even though throughput will increase for like so but 16 is the best. And during sampling, what they saw was we could do like a little bit lesser also. Like even though the model was trained with 16 block size, you could try 8, and 8 still gives you not degrading level performance. It will give you good performance. So yeah. So again, coming on to the limitations of the paper. So still, even though like they tried sort of like a hybrid architecture where AR is used for context and then denoising network is there. The math and code still shows that there is moderate degradation compared to AR baseline. In terms of memory, we have to now load both networks to do this 2 tower setup. So that is also not ideal. Then comes adaptation cost. Still 2.1 trillion parameters tokens being used to train the pre-trained model. So again, a lot of training is being done. Then block size rigidity. So sampling block size should match the training block size. So again, that issue is there. Then they only demonstrated on a 30B class model. So nobody has done it on a larger model or a smaller model. So it's still open there. And we don't even know like what happens if there is an asymmetric tower. So right now it's like very same tower. What happens when it's an asymmetric tower? We don't know yet. Conclusions, decoupling the roles between AR for context and trainable diffusion denoiser beats the single network diffusion architecture that is out there. And layer aligned cross attention was used here so that the context is being carried into the denoising the network. Then small addition matters. So adaptive layer normalization does help. So that has been shown through ablation study. Practically, there is a 98.7% of AR quality that is being achieved here with almost 2.42 times the wall clock throughput of 30B hybrid model. So that is very good. The big picture is that mass diffusion as a decoding adaptation for existing pre-trained AR models is not yet done. So yeah, they have done that, and that's interesting. So yeah, thank you. Any questions?
Soham will be talking about graph language models. So the idea is that graph language models appear multimodal, but the paper that he worked on shows that many succeed by relying on either text or graph structure alone, which is like essentially cheating, but with little cross-modal, that has like very little cross-modal reasoning. So they have worked on a benchmark which is called Clegger. You pronounce it Clegger, and like a data scaling framework designed to like require genuine graph language integration and expose like real multimodal reasoning ability. So over to you, Soham. Let me just check. Just make sure this thing works fine. Cool. Take it over.
Yeah. Greetings, everybody. Till now, we have been talking about diffusion language models. So let's shift our focus to graph language models. So this work we did across like almost 1 year back when during my time at IIIT Hyderabad. This work was done with Hari, Anirudh, Akshit, PK, and Chirag. and was recently accepted into the ACL 2026 and was accepted into the new RIPS and PGML workshop last year. So let's get started. So let's cover some prereqs about graph machine learning. So in traditional graph ML, you work with GNNs. And what GNNs do is they actually learn a structure or a representation on a graph. So you have nodes, and these nodes are connected to other nodes, and these nodes are neighbors, and these nodes are then connected to other nodes. So what we are trying to learn using a GNN is basically the structure and semantics of the entire graph. So you have a node and it has its own embedding, and across k hops by using message parsing, what we are trying to do is learn the neighborhood of this particular node. So after n hops, what would happen is this node would have information about itself as well as its neighboring. So after k hops, in general, you are capturing the structure as well as semantics. In graph ML, in graph neural networks, we traditionally work with something called as text attributed graphs. So these are undirected graphs where each node has some textual attributes, and the edges between two nodes also have textual attributes. These are the features basically of the nodes and the edges. And in this example, I've taken the archive data set where you have each node as the paper, and the edge between them depicts the citation network. And in graph ML, you typically have two tasks. One being the node classification, where you give the node representation to the graph neural network, apply a classifier on top of it, and ask what class does this node belong to. And the second task is link prediction, which is an arguably simpler binary classification task where instead of giving one node, you give two nodes and ask, okay, whether there exists a link between these two nodes. And the data sets which have been commonly used across the GraphML literature are Cora, Sightseer, computers, etc. So recently, in like 2 to 3 years, what has happened is there has been this new paradigm that has come up, which is graph language models. So people who must have seen vision language models, the idea is pretty much the same. What people are trying to do is take a graph or a graph representation, pass it through a graph encoder, get the representation of the node or the edge, and pass it through a linear projector, which gives us some tokens, which can be passed along with some textual context and the question in the large frozen large language model, which is responsible to give you the answer. So in this case, an example would be you get the token representation. So you take one node, project it into 10 different tokens, into the of D model size, which is basically the embeddings, language model's embedding dimension, and then you pass some context of that particular node, which is basically the abstract or the title of the paper, and then you ask a question, okay, what category does this particular node belong to? Yeah, so the prediction equation looks something like this, where the node comes from the graph and the graph encoder captures the node embedding. Then you pass it through the projector, which is responsible for giving you the graph tokens, which you pre-concatenate with the context tokens and the question tokens, which as a whole is passed through the large language model, frozen large language model, to actually give you the answer. So at this point, you must have started to wonder, okay, we have something very powerful as a graph language model, which actually is multimodal in nature. You have a graph modality, you have a text modality. Then why are we still focusing on traditional ML node classification or link prediction tasks? This is what we also felt during that time. And that's why we decided to do this study, because we felt that the science of actually creating newer and newer models has started to outpace the science of actually evaluating them. So to actually understand if the current evaluations are sufficient for capturing the true multimodality of graph language model, we ask two questions on the current evaluations. Are current evaluations data set single modality sufficient? So basically, if we take the data set and we just remove one modality out of it and then train a model using just one modality, are we able to achieve a performance which is competent enough when we give access to both the modalities? And the second question what we ask is, okay, can we actually tell if the GLM is actually using both the modalities to answer the given question? So the experimental setup looks something like this. We take all the tasks which have been used in every paper of graph language models, which is node classification, link prediction, and something called as the zero-shot cross dataset transfer task. It's nothing but just take node classification, train a GLM on dataset A, and during inference time, you pass dataset B as a graph as a node, and then you predict what category the node belongs to. We test GLMs like TGLM, graph token, graph prompter with 2 different LLM backbones so that to get some variety and some idea of data size scaling. The only difference between all these GLMs is the encoder that they use, graph encoder, and whether the graph encoder and the projector were jointly trained or not, jointly pre-trained or not. So we create 2 unimodal baselines to compete with the multimodal graph language model, one being plain graph neural networks, GCN, GAT, graph sage, and the second being something called as the soft prompted LLMs. So to actually answer the question, what we can do, like I said, just strip one modality at a time and train a unimodal model and see are we able to achieve a performance equivalent to the entire graph language model, which has access to both the modalities during training. So a GLM, you have the graph tokens concatenated with the context and the question. It gives the y hat as the output. Language only baseline is we replace this entire graph tokens. We just remove those graph encoder, the projector. We just take 10 cross D model size randomly initialized vector, which acts as a soft prompt, and we just train the LLM with the 10 cross D model vector. So the LLM is not getting trained, only the vector, the randomly initialized vector is getting trained. So this is something which is called as a soft prompt. And this has only access to the text. So what we're trying to do is, is the soft prompt able to steer the LLM towards the right answer, even if we don't give it the graph encoding information. And the graph only baseline is just a simple GNN. And surprise, surprise, if we look at node classification as a task, you can see that GNNs are actually thrashing the GLMs across like all 6 data sets. Even the soft prompted baselines are on par, at par with the GLMs. But surprisingly, if you look carefully at the bottom right corner, you may seem that, okay, these soft prompts are not actually performing good on these 2 particular data sets, but across all the other data sets, also link prediction as a task and zero-shot transfer as a task, we see the same exact pattern. So what is happening in this particular case? So we decide to dive a bit deeper, and what we do is simply take the projector outputs, which is basically the 10 graph tokens, and we just train a simple linear classifier probe on top of it. So what we are doing is just removing LLM out of the equation, just looking at the graph tokens and trying to understand if the signal needed to solve the task fully is present in those 10 graph tokens. And what we observe is actually this is the case in all those GLMs. So the graph tokens are essentially acting as soft prompts, and they don't contain any graph specific information in some sense. So this graph, on y-axis you have the GLM accuracy, on the x-axis you have the probe accuracy, and you can see it's almost the same for both these data sets across the GLMs, and in some cases actually the probe accuracy is better than the entire GLM accuracy, which is surprising. That means the LLM is essentially acting as a very expensive decoder head and just adding noise and polluting the results. This is just summarizing what I talked. So you have the soft prompts, you have the textual context, the graph, the query, soft prompts, you get a prediction. This is the GLM, graph tokens, text tokens, question tokens, you get the prediction. Predictions are almost the same. Also, if you probe these graph tokens, the predictions are almost the same. So what we are trying to analyze and actually exhibit here is current benchmarks which are being used to test graph language models. You can just use a single modality and game them, and you don't need access to both the modalities. So we don't even know if the GLMs truly combine both of them to achieve at the right answer. So we need a benchmark which essentially fuses both the modality or tests fusion of both the modalities, because the current evaluations are not enough. So from this analysis, what we can establish is we need 3 requirements for a multimodal graph language model benchmark. One being the structure dependency, so that the structure is an essential part of the question, such that the GLM is able to answer it. The second is you should have a natural language questions, not like a classification question where you can actually train a GNN, just train a GNN. So, and third being the compositional complexity, where language and graph both together should be used to answer the question, and a single modality should not be allowed. So if you think carefully, we have been closing towards questions which other multimodal language model benchmarks are. So if you look at Clever or any vision language model benchmark, you have an image, you have a question, and then the question is asking what is happening in the image. So we're trying to go near that particular paradigm even in graph language models, because this is something which was not available before. So hence we introduce Clegger, which is compositional language graph reasoning. What we do is we deterministically create a pipeline where we have 34 question templates, and we actually randomly initialize some graphs and create graphs, create a graph creation pipeline. So it's a completely synthetic benchmark. Each node here has multiple textual attributes. Each line edge has multiple textual attributes. We have multiple graph sizes, and it's a graph level task and not a node level or edge level task. We also have node level, edge level, node level, edge level, and subgraph level questions. If you can see that, okay, is this particular node part of a cycle? Which stations does this particular edge line pass through? What is the shortest route from node green to node blue, avoiding node red? So basically these questions are trying to stress the multimodal language model reasoning, that you need to understand the structure as well as the question in order to answer the particular question. Yeah. So this is just talking about how we create the benchmark. And since it's a synthetic pipeline, you can actually scale this pipeline for millions of graphs, and this actually becomes a data scaling pre-training recipe for any future graph language model you create. So this is just Clegger at glance. We have 500 synthetic sub-WAN networks. We also create something called as the Clegger computer networks, only to test particularly the claim that other GLM models make, which is basically the cross data set transfer. The only difference being the textual attributes in computer networks is slightly different than the sub-WAN networks. And all of this is synthetic, so there is no pre-training leakage as such. So because if you can see, LLMs today are trained on a very large corpora, so there's a chance that LLM has actually seen archive, Cora, Sightseer, all these data sets in its pre-training mix, so we don't even know if the performance is coming from the pre-training or the GLM training. Yeah, so at this part of the paper, we just try to evaluate the GLMs along with the unimodal baseline, which is soft prompt in this case, on these 3 particular questions. So we want to see if does incorporating structural informations into LLMs help on tasks that need it. So Clegger, as we saw, it needs a fusion of both those tasks. And GLMs, we want to see, okay, GLMs are claiming this particular promise. Are they actually able to show performance greater than soft prompts on Clegger? So we add gRetriever as a new GLM. We add 5414B as a scaling backbone. Yeah. So if you are able to see, sorry, the graph is small, but all the performance across soft prompts and all these GLMs plateaus around 45-50%. The GLMs are at par and performing at the same level as soft prompts. So GLMs are essentially providing negligible gains over unimodal baselines, even in a benchmark that does require multimodal fusion. Similar results for scaling or transferring, we can observe this exact same pattern. If we look at a soft prompt or a GLM, we see the same performance. So the takeaway to here is on Clegger, a benchmark we designed to evaluate multimodal integration. GLMs are actually achieving a low performance together as with soft prompt baselines, and soft prompt baselines are also performing at the same level of GLM, both of them performing low. So GLMs, what they bring in the promise of fusing the multimodality is not actually happening. So in first part, we see the evaluations are not that great, and now we are saying that, okay, even if you have a evaluation which tests multimodality, the GLMs are not true to their promise. So this is just the takeaways of the entire thing. Thank you. Any questions? I hope you found the talk interesting.
Cool. Thank you so much, Soham. Next up is like one paper which is like very interesting and like super interesting how they came with that intuition also. I think that's pretty cool. So Dognosis is a paper that talks about like training dogs to like detect cancer from breath samples. So they experimented across like over 3,000 people in Karnataka, and that offers like a fast and non-invasive screening method to detect cancer across like different categories. And then they combine it with Bayesian modeling, and the system shows promise as a low-cost triage tool for resource-constrained settings. So over to you, Akash. Please come in, and Ashwin.
Yeah, thanks so much for Kautak and Conscious Engines for inviting us. I'm Akash, I'm the co-founder and CEO of Dognosis. Ashwin here is an engineer with us working on computer vision models. And I'm super excited to talk about what we do in general, but also go a bit deeper into some of the math and also some of the machine learning we're doing, which we generally don't get to talk about as much because most people are like, oh, cute dogs smelling cancer. That's kind of like occupies a lot of like mental real estate. And I'll talk about that quickly, but I do want to talk about some of like the Bayesian fusion work we're doing. Some, it's still very preliminary, but we think it's already quite elegant. And Ashwin's been doing a lot of work with computer vision and how we'd be integrating that into our fusion models. And I think that's what you guys could really help us actually maybe think about new lines, and very excited to chat about some of that stuff. But I'm just going to set some of the background and kind of the context, because I know there's quite a bit here. I don't know how many people before coming here or reading about Dognosis in the event description knew that dogs could detect diseases. Show of hands if you knew about it before. Okay, quite a few people, that's cool. I'll just talk about some of the science here in a real speed run. So, we know for a while that breath carries a complex cocktail of VOCs, volatile organic compounds for short, or VOCs. And these are from various metabolic and other processes in the body. And it's throughout the body, not just in the lungs, because the blood carries VOCs everywhere, right? We know for about 30 years now that diseases change this VOC profile in a pretty consistent way across individuals. It leaves a scent signature, if you will. And in the same 30 years of time, we know that we can actually identify this scent signature with the right sensor, enough compute, and the right algorithm. And on the right here is one of the most sophisticated such sensors, a mammalian olfactory bulb with all the receptors that they have. And that's what dogs really, why they're so good compared to machines. In fact, when you compare just in terms of limit of detection, dogs can sniff in parts per trillion from the literature that we know. Our best chemical methods like GCMS are detecting in parts per million. So there's a 6 order of magnitude difference between what dogs can do and what machines can do. That has increased a bit with latest techniques, but it's still in the parts per billion range. So the dogs have the upper hand in just limit of detection, and they do a lot more. And that's really allowed them, for the last 20 years to detect all kinds of diseases, starting with the UK non-profit medical detection dogs, who are close collaborators. They've actually shown that dogs can detect 28 diseases and counting. That's a Guinness World Record for the most diseases an organization has been able to train dogs for. This is multiple types of cancers, infectious diseases, neurodegenerative disorders. COVID-19 was a watershed moment. That's when I learned about it. 60 countries around the world train dogs to sniff COVID. And the accuracy is often really good, right? It's above 90%. Sure, there's small sample sizes, but they still seem to do this pretty consistently. And so the question is, wait, where are the real disease-sniffing dogs, right? And my co-founder Itamar and I both felt that actually what was the challenge wasn't the dog's nose. It was actually the human-canine communication loop, where humans have to interact with this alien species in some sense. We have to train them to give us a special response, and we need to read that response. This takes about 12 to 15 months of additional training. It requires a special human, a special dog, there's a high chance for communication error and bias to creep in. And so people have always said, oh, this is hard to scale. Let's try and build an electronic nose. The dogs can do it, but what are we going to do? But the humans aren't really necessary in this equation, right? We're kind of just getting in the way. The dogs are able to do it. Their noses are great. So we just said, like, let's replace the humans, right, with AI, which is, of course, the zeitgeist now. We can train AI to read dogs from their brain waves, their sniffing patterns, and their body language. And suddenly you can translate what's going on in that canine compute into digital bits that you can now apply data-driven processes around. And when we couple this with an ability to write back to the dog, so we built a robotic workstation that allows us to present samples and rewards without a human in the loop, we're suddenly able to create this closed loop olfactory inference system where we're reading from the dogs with sensors, we're predicting the dog's state with machine learning models, we're writing back to the dog with samples and rewards to then have this whole system that operates without humans in the loop. And this allows us to do what we're currently focused on, which is multi-cancer early detection, or MCED as it's called, from breath at scale, where an individual breathes into a face mask, seal it in a bag, ship it over, a team of dogs and AI evaluates it for the presence of multiple types of cancers, with the overall goal of creating dog millionaires with a great work-life balance. So in a single 30-minute session, a dog can sniff 250 samples very comfortably because a dog has a sniffing frequency of about 4 to 7 hertz. 30 dogs in a year can then do 1 million samples, with each sample being read by 3 dogs. And if you charge it fairly affordably, each dog is pulling $3 million or 8 CR. They don't know what to spend that money on, so we can take a fee from them, and that's how we make money. So all of that is kind of the background of the company. What we did in the last year and a half was a phase 2 study. In medical parlance, phase 2 is essentially for diagnostics. You know the labels, and you're trying to predict them in a blinded manner, whether you can tell the labels apart. And this was published a few months ago in the Journal of Clinical Oncology, or JCO. It's essentially the #1 cancer journal in the world. Oncologists all around read this journal to update their practice, like what chemotherapy they should be prescribing or what new diagnostic they should be taking seriously. And what we did in the study was essentially we collected a sample. It was a face mask worn for 10 minutes. We had a training set and a test set. So we had about 3,275 participants volunteer their time, giving us a sample. We split it into training and testing. This is kind of what it looks like to be collecting these samples in community camps and hospitals around Karnataka. And we had 6 great hospitals we worked with, including Narayana Health, St. John's, and Aster CMI here in Bangalore. And this is kind of what the workflow looked like. We collected, we recruited participants, split that into the training and the test set. In the test set, we had 283 cancers, and the remaining were controls. Here, a case is essentially someone who's been confirmed to have cancer with a biopsy, which is the gold standard, but they haven't started treatment yet. So there's a 1-week window generally when this person is in the hospital awaiting treatment. And controls were essentially healthy attenders, patients with other chronic conditions, or people with benign tumors. So it was a grade of kind of easy to very difficult to discriminate against. And this is kind of what the breakdown looked like. The point worth highlighting here is in absolute numbers, the number of people with things like tobacco chewing habits or comorbidities was essentially the same in both cohorts, even though the relative distribution was different because, of course, more people chewing tobacco end up with cancer, but you still have the same absolute numbers because we had more controls. So that's how we are able to tell, okay, the dogs are actually sniffing cancer and not just tobacco chewing habits. And all of this was done on a platform, SniffSpace version 1, where we had these barriers, infrared sensors, we had a QR code reading samples, and importantly, during the blinded sessions, the trainers who were logging indications were not aware of the sample identity. They just knew there was a QR code with a sample tag. Only after logging an indication into our database were we then unblinded, because we're still rewarding the dogs for the correct indications. But at the point of logging the indication, the trainers were unblinded. So the clever Hans kind of effect can be accounted for. So this is what it looks like in practice. We have 2 of our dogs now, Whiskey and Cheetah, kind of just showing what this looks like. So this is Whiskey. She's sniffing one of those face masks in each one of those ports. All the greens are the controls. The red is someone with cancer. She'll sniff the cancer sample and she goes back to the platform because she's like, I found cancer, give me treats. And that's basically the indication, and the strength and confidence of that movement is what the trainers are parsing, and all the fine-grained body language. While this is happening, they're wearing a helmet and a harness that measures their brain activity through EEG. It's fully non-invasive. A respiration sensor that's measuring their thoracic cavity movement, and then a bunch of cameras that we're doing cool stuff with, which Ashwin is going to talk about in a bit. And you'll see Cheetah do it one last time, and as you can see, it's like super quick. She takes half a second or less to actually decide whether a sample is cancer or not. She's like, okay, found cancer, go back, where's the treats? So I'll just briefly talk about this. Ashwin is going to return to this, but what we did was each sample was actually evaluated by multiple dogs, and we also computed a prior for each sample based on the participants' covariates. So we collected about 28 variables, including sex and age, behavioral exposure through tobacco habits, comorbidities, the presence of persistent symptoms, family history. That gives you the prior for whether that person has cancer. And we used an XGBoost model to actually compute this prior, form the training set, applied it on the test set. And then each dog is giving a likelihood update, which is tempered by their historical performance, their sensitivity and specificity, and then fused in this kind of Bayesian framework, which allows us to then aggregate various dog indications for a given sample to give us a posterior. And then we come up with a threshold based again on the training set to then give the binary classification of whether it's cancer or not. And when we did that, and then we looked at kind of what comes out of that test set, for the different decision thresholds, you have the sensitivity and specificity metrics. And based on kind of the training set calibration, 0.2 was the threshold that we chose, which ends up with this 91% specificity and 90.8 sensitivity. And that sensitivity held across cancers and stages. So across the different cancer groups, we had 7 and 20 total types. So head and neck, breast, upper GI, lower GI, the dogs were able to consistently perform around that 90% sensitivity. And across stages, and this is the most important thing, if you want to detect cancer early, you need to detect it early in stage 1 and 2. So the dog's accuracy held above 90%. And just to give a comparison, there are other multi-cancer tests out there that look at so-called liquid biopsies. They look at cell-free or circulating DNA that's shed from tumors, and then you apply next genome sequencing to actually tell you, are there methylation markers or other markers of that DNA being from a cancer sample. And the companies, public companies like Exact Science and Grail, Exact Science was bought by Abbott recently this year for $28 billion. They've been around for 20 years. Their stage 1 sensitivity is 25% across cancers, and overall stage 1 and 2 sensitivity across the liquid biopsies is below 50%. So this is a smaller study than what they've done, but it does hold true for the literature in general. The dogs are 3 to 4x better than these $700 to $1,000 tests that people have spent a lot of time developing. And it's just, again, that limit of detection of the dogs, the parts per trillion, is so sensitive that they're able to do this. So specificity held across recruitment settings and comorbidities. So it's not just sickness that the dogs are detecting, they're detecting cancer specifically, at least it seems like. Accuracy held across cohort variables like age, sex, tobacco habits, comorbidities, fasting status. The interdog variation was not significant to performance. So when we looked at the interclass correlation coefficient, it was 0.019. So less than 2% of variation was because of the dog identity. And you can see the dogs are performing pretty similar across the board. There's some variation, but after they go through our training and calibration, it's not significant. And we also did a few cool things where, everyone always asks, like, oh, what if the dog has a bad day? We simulated that. So the dog has a bad day, it fires at random, but the overall performance stays stable because of that Bayesian framework. What if the dog is sick and doesn't work that day? We simulated that. So it's pretty similar. The area under the curve remains stable for that test set. So we had a small paragraph in the discussion section. This was last year when we did the study, where we said we'd extend this fusion framework with additional behavioral and physiological signals, including computer vision derived sniffing dynamics. We showed that this vision augmented fusion performed at almost the same level as our overall model. And we've made a lot more progress since then. The idea is you don't just have to take a trainer's indication. Trainers are great. They can read a lot from a dog's body language. But we can probably do better is the assumption and the thesis. If you give the dog or the model more information than a trainer can parse.